Polar form of complex numbers is what we're looking at today. All right, so let's kind of do a little quick review. Polar form of complex numbers. What we've done so far is look at which form of complex numbers? Which form have we looked at so far? What did we call it? Standard form. Thank you. Standard form of a complex number is also known as, and we haven't called it this yet, but we'll kind of give you this because you'll see this form used. Rectangular form. The reason it's called rectangular form also is because we can use the A and B to kind of a rectangular format, right? We can look at the graph of it in a like a rectangular coordinate plots. A plus BI, in the complex plane would be equivalent to A comma B in the rectangular coordinate plane, or the just regular XY plane. But rectangular form is also another name for standard form. So you'll see this in complex number theory. This is one of the confusing things about working with complex numbers and vectors, is that there are a lot of different names for the same thing. For example, the absolute value of a standard of a complex number, the absolute value of A plus BI, which we said is the square root of A squared plus B squared, is also called the radius. It's also called the, does anybody remember the other numbers, the other values we gave it to it? The absolute value is called the radius. It's called the norm. It is the hypotenuse of the triangle form of that. It's called the magnitude of the number. Another one in vector form, it's also called the modulus of the number. Okay, so lots of different names for the same thing. Okay, so the radius is the absolute value. It's also equal to the norm, the magnitude, the modulus of the number, the what else? I think that's about it. But there's a lot of different names for the same thing. So standard form and rectangular form are synonymous. Okay? Polar form of a complex number is related to standard form. So A plus BI equals, here's polar form, R, that's the radius, we already know what that is, times cosine of theta plus I sine of theta where R is the radius of the number That's also the absolute value, right? The radius of the number. And we just need to know what theta is, right? What's theta? What do you think theta is? Anybody got a hint? Guess? No? Theta is an angle, right? It has to be an angle to be cosine of theta. So it's the angle, and theta is the standard position angle. We're calling that standard position starts at the positive x-axis. Oopsie, angle that passes through the complex number. Okay. Theta is the inverse tangent of B over A placed in the correct quadrant. Okay? Theta is the inverse tangent of B over A placed in the correct quadrant. So let's make sure that you have, sorry, puberty. Make sure you have the correct, it's the second puberty. Go through it when you get about 50, my age. Yeah. Gets worse every time, doesn't it? All right. Okay, now we already know what radius is. So this is the polar form of a complex number. R times cosine of theta plus I sine of theta. Where R, we already know what R is. R is the radius of the number. And theta is the inverse tangent of B over A placed in the correct quadrant. So again, we're going to be talking about reference angles and quadrants. Place this reference angle in this quadrant, and it's repetition of what we've been doing since test number 1. So that's the polar form of a complex number. Toward the end of the lesson, I'm going to show you why we're using this form of a complex number. This form of a complex number makes some mathematical operations a whole lot easier. Okay? Any questions about this before we look at an example? So theta is the direction of the angle. Theta is the direction of the point. Now, keep in mind that I've been telling you all along that this is related to vector operations, which is what we're going to do in our next, our last little unit of the year. Every vector has two quantities. It has a direction and a magnitude. All right, direction and a magnitude. Here is the direction, and here is the magnitude. The radius is the force or the size of the vector, and the angle of heading is our theta. Okay, so let's have a look at an example.
Which one's direction?
The theta, the angle. Okay, here we go. Now, what we're going to do here is write this complex number in polar form. Let me see if I can maximize that for us. Maximize. No? There we go. Okay, this complex number is in standard form or rectangular form. The first thing I'm going to do is what? What are we going to do first? What do you think we should do first? Well, we could do that. Don't we have to place this angle in the correct quadrant, right? So the first thing we're going to always do is graph it, which is something that you guys did on the quiz yesterday, and I'm assuming you did quite well. It's not a difficult skill. Where's negative 4i on the graph? Down 4. I don't want that. I want color here. Now, sometimes we can see the angle or the direction of the point without even using the inverse tangent. What's the angle in standard position that gets us to here? What is that angle? Degrees. Oh, man, y'all got to wake up. 270 degrees. You agree with that, Taylor? What about it, Mary? You got 270 degrees. So we can see in this one real quickly. Charlie, what's the radius of this number? How far is it from the origin? 4, right? The radius is 4. Distance from the origin. We don't even have to use the you can see the distance in this one. If it's on the x or on the imaginary or real axis, then you can see its distance from 0. The heading is 270 degrees. That's the angle that passes through that complex number. Standard position angle that passes through negative 4i is 270 degrees. So negative 4i in polar form is the radius, which is 4, times the cosine, 270 degrees, plus I times the sine of 270 degrees. That's it. Now, Daniel said, do you leave it like that or do you have to work it out? Because we're talking about polar form, Daniel, remember when we get to this, a plus bi, polar form will always look like this. R times the cosine theta plus I times the sine of theta. So if our goal is to write it in polar form, that's what we're looking for. Okay, now, what you said, working it out, if you work it out, you can't always check to see if what you've done is correct. You can do that pretty quickly. You can check your answers because we know that the cosine of 270 degrees, remember cosine is the x coordinate of the point. The cosine of this angle is 0. The sine of the angle is negative 1. The sine of 270 degrees is negative 1. And what do we get if we multiply that together? Negative 4i. Okay? So this does confirm that we started with negative 4i, we changed it to polar form, and if you evaluate the polar form, you get negative 4i. That just confirms that the polar form that we did is correct. And you can use your calculator for these. We'll be doing a lot of calculator work finishing up the year, but you could punch in cosine of 270 degrees, you get 0. Sine of 270 degrees, you get negative 1. Or you can look on your unit circle also. So writing a number in polar form involves finding the absolute value of the number and the heading of the number. All right, so let's do another one. Negative 3 minus 3i. We're going to sketch the graph and write it in polar form. The reason we need to sketch the graph is because we have to put our angle in the correct quadrant. Nice of you to join us, Mr. Miller.
You said you were going to skip this
Okay. All right. What quadrant is this in? What quadrant are we in? Third quadrant, right? Now, this is another one where we really don't even have to use trig. Right? Can somebody tell me what this angle is going to be? No, it's not 240. What kind of triangle have we formed here? Let's go back to week 1. It's a right triangle that is left 3, down 3. What kind of triangle is that? If the legs are congruent, it's a 45, 45, 90 triangle, right? So this is in standard position. What's that angle? 225 degrees. All right? Now, let's just suppose for a moment that you didn't recognize that. Then we'd have to go through the steps of the process. The radius of our number, r, is equal to the absolute value of negative 3 minus 3i is negative 3 squared plus negative 3 squared. That is the square root of 18, which is equal to 3 times the square root of 2. Isn't 3 times the square root of 2 the hypotenuse of a 45, 45, 90 triangle with legs of 3? It is, right? So you could use your special right triangles or you can use the trig. Now, theta is the inverse tangent of b over a. That's -3 over -3. Using your calculators, if you had to, the inverse tangent of 1 is 45 degrees. 45 degrees in quadrant 3 is 225 degrees. So theta is 225 degrees. And my complex number, -3 minus 3i, equals the radius times cosine of 225 degrees plus I times the sine of 225 degrees. And that is the polar form of that complex number. If we wanted to write it in radians, you could. 225 degrees is 5 pi over 4. We're going to be doing radians quite a bit when we start actually applying this. We're learning this skill for a reason. It has something to do with what I told you guys early on in this unit, that we were going to use trigonometry to find all of the fifth roots of 1, for example. All 5 fifth roots of -2. So there's lots of those. There's 5 of them to be exact. And it involves polar form. Okay, let's look at another one. This is pretty easy. Let's look at one where we have to use our calculators to find out the values. -1 plus 3i. We want to sketch the graph, write it in polar form. Polar form of a complex number is r times cosine of theta plus I sine of theta. Grab a calculator if you don't have one. Charlie, would you get Miller a calculator, please? And Holt. Interception. Get the Gargasmeister one. Okay. Are y'all ready? Where do we start? Where do we start? Graph. Why are we graphing it? Because we have to place the angle in the correct quadrant. Okay, so -1, 3 is right here. So we need to find the radius, which is just going to be the distance from the origin. And then we need to find the angle that goes from there to there, standard position angle. That's my R value, and this is my theta value for the polar form. Okay, let's find R first. We did this yesterday in a quiz. R is the absolute value of that number. Square root of -1 squared plus 3 squared equals, we have a radius value of the square root of 10. Okay? To find our reference angle for theta, we do the inverse tangent of b over a. That's 3 over -1. Or you could just really do 3 over 1, because all we're doing is finding a reference angle here. And what does that give us? Let's keep our answers to the 10th place in degrees. Make sure your calculators are in degree mode. What do we get? 71.6 degrees. Now, keep in mind that that is our reference angle, right? That's the angle right here. This angle right there is 71.6. So how do I find theta if that is 71.6? Subtract it from 180. What is 180 minus 71.6? Theta equals 108.4 degrees. That's the magnitude and the direction. So if we're talking about a force vector, the magnitude of this force vector is the square root of 10, whatever. Pounds or tons or grams. That's the force behind it. And then 71.6 degrees in the second quadrant is our heading. So this complex number, -1 minus 3I, is equal to the radius times the cosine of 108.4 plus I times the sine of 108.4. Bless you. Okay? Now, really, if we were being very, very technical about this, because we used a decimal approximation, we could use an approximately there, because we approximated that angle. Just to see what I'm talking about, take your calculator and multiply the square root of 10 times cosine of 108.4 degrees. What do you get? What'd you get, Taylor? -0.998. Now that's really, really close to -1, right? So -0.998 is what we got. What did we start with? We started with -1. So when we approximate that angle, we lose a little bit of precision, but that's 2 1,000ths. You know, that's pretty close depending on what kind of units we're working with. All right? Let's try one on your own. Try this one. 2 minus 5I. We want to find the radius, absolute value. Bye, Caitlin. Have a good day. Oh, you almost snuck out. Let's see. You done? Hold.
With my snack.
First things first. 20 minutes into class and Holt's ready to start. Okay. We need the radius of the number, which is the absolute value, and we need the complex number. Okay. About done. 2 - 5 is in the quadrant, fourth quadrant there. So we're going to be dealing with this quantity. Now, we could use that angle. As long as it's in the standard position, I don't care if you use the negative angle either. I'm happy either way. I may be breaking some type of rule by saying it can be either one of those, but for our purposes, for what we're doing, this is good enough for me. All right. What'd you get for the radius, Miller? Okay. Daniel, what'd you get for the radius?
Root 29.
Square root of 29 is correct. All right. And theta, what do we get for theta?
248.
Inverse tangent of negative 5 over 2 would give us what?
248.
Well, what's the actual tangent value that you get when you do this? Negative 68.2. So we could actually, in this problem, we could actually use that value and say that 2 minus 5i is equal to square root of 29 times the cosine of negative 68.2 degrees plus I times the sine of negative 68.2 degrees. If you put it as a positive angle, what'd you get, Charlie, for the positive angle? You subtract 68.2 from 360, what do you get?
Mine's rounded differently, but I have 248.2.
It's
291.8. 291.8 degrees plus I times the sine of 291.8 degrees. So I'll take either one of those. It's a nice quadrant 4 angle. We can get there in a negative direction. Can you handle it? You need to see one more, or are you good? Daniel, you good? Good. All right.